Hello and welcome to lesson number 17, which is the second part of derivatives. Now, unfortunately, due to the size of this lesson, there is of course going to be a third part. And if you haven't watched the first part already, go and check this first part over here. The link is in the top right. Check it out and then come back. So, derivatives part 2. As a recap, let's talk about what we talked about in derivatives part 1. So, as a recap, what we did was first discuss the first principle definition of the derivative, saying that dy by dx was the limit of the function as dx approaches 0 of f of x plus dx minus f of x by dx. So we discussed that dy by dx was the limit as dx approaches 0 of a function evaluated at x plus dx minus the function evaluated at fx divided by dx. Next we discussed some common rules of these derivatives and some common derivatives. So first we discussed the derivative of x to the power of n dx. We discussed this and we found that this was equal to n times x to the power of n minus 1. Next we discussed that if you have a derivative of k times some function fx, something like this, the derivative of this is going to be k times the derivative of the function by itself, fx dx. And then we found another one saying that if you have a function that is a sum of two functions, let's say d of f of x plus g of x dx, we can break this into the two derivatives of the derivative of f of x dx and then plus the derivative of g of x dx. At this point we had sufficient knowledge in order to find the derivative of any polynomial function, because a polynomial is just a sum of terms with coefficients and x powers in front of them. So here this thing can deal with the x powers, this can deal with the coefficients, and this can deal with the sums. So you first break the sum of terms into individual derivatives, take the coefficients out using the second rule, and then finally take the derivative using the first rule, and then put it all back together to get the final answer. Then we talked about some common derivatives that are the sine, cosine and tangent derivatives and their inverses derivatives as well. So we talked about derivatives of sine x dx, we talked about the derivative of cosine x dx, we talked about the derivative of tan x dx, and we talked about the inverses, which are the derivative of cosecant of x dx, the derivative of secant of x dx, and the derivative of cotangent of x dx. The derivative of sine of x was found to be the cosine of x. The derivative of cosine of x was found to be the negative sine of x. The derivative of tangent of x was found to be the secant squared of x. Symmetrically, the derivative of cotangent of x was found to be negative cosecant squared of x. The derivative of cosecant of x was found to be negative cosecant of x cotangent of x. And the derivative of the secant of x was found to be the secant of x times the tangent of x. This is all we did previously. Now let's go on to some new rules. Other than this, there are 3 more rules that we need to know before we continue on to further derivatives. The first rule is the product rule. The product rule states that if we have a product of two functions, let's say d of f of x times g of x, then the derivative of this is equal to the derivative of the second function times the first, so f of x times the derivative of g of x dx plus the first function's derivative, so d of f of x dx multiplied by the second function gx. Writing this in prime notation is more handy because it's shorter and it's much easier to understand. This is f of x times g prime x plus f prime of x times g of x. So basically the derivative of the second function times the first plus the derivative of the first function times the second is equal to the derivative of the product of the two functions. The first thing we're going to do in this video is to prove this identity here. So in order to prove this, what we're going to do is consider the left hand and right side separately and try to get from one side to the other. We're going to actually start from the left side in this case and try to get to the right side. So writing the left side in terms of its basic first principle notation, the derivative of f of x times g of x dx according to first principles would be the limit as dx approaches 0 of this function evaluated at x plus dx. So f of x plus dx times g of x plus dx over here. F of x plus dx times g of x plus dx, and then minus the function evaluated at x. So here f of x times g of x would have to be subtracted here. So minus f of x times g of x. And then all of this needs to then be divided by dx. This is the first principle definition of the derivative of the left hand side. What we're going to do now is actually to introduce a term and subtract it immediately. We're going to add a term and subtract it immediately because we're trying to look and turn this thing into a form that will give us this thing on the right here. We want to get to this right hand side. In order to do that, what we're going to do is generate a term in the middle and immediately remove it. The term we're going to generate and remove immediately is going to be f of x plus dx times g of x. So to do that, I'm going to take this equal sign to the left here, so we have space. This is going to be the limit as dx approaches 0 of the original term, which is x plus d f of x plus dx times g of x plus dx. But now I'm going to introduce a term. I'm going to introduce negative f of x plus dx times g of x, and then I'm going to add that same term again. So f of x plus dx times g of x minus f of x times g of x. So here we subtracted this term and we added this term again. Adding and subtracting the same term does nothing. So here we have the same exact expression we had earlier. It's just that now we have added and subtracted a term that wasn't there before. Still, the numerical value of this thing is going to be the same. It's just that we have added and removed something. And then this whole thing needs to then be divided by dx. The next thing we're going to do is use the law of limits, saying that we can split this into two pieces. If you don't remember that, check this video over here on limits. Here, what we're going to do is split this thing right down the middle like this. Splitting it right down the middle, what we get is the limit of the first part, which is the limit as dx approaches 0 of, considering only this part and taking it separately, we have f of x plus dx times g of x plus dx, minus f of x plus dx times g of x, all divided by dx, plus the second limit, which is the limit as dx approaches 0 of, and over here what we have is this part here. We have f of x plus dx times gx minus f of x times gx all over dx. So we have f of x plus dx times gx minus f of x times gx all divided by dx. Now here what I'm going to do next is, on the left side I'm going to factor out this f of x plus dx that both of these terms have, and then I'm going to break this limit into two pieces. Similarly over here, I'm going to take this g of x factor over here, take it out, and then I'm going to break the limit into two pieces. We're going to do that in two steps. First we're going to factor out, then we're going to break the limit into two pieces. So on the left here what we have is the limit as dx approaches 0 of, factoring out the f of x plus dx, we have f of x plus dx multiplied by, and what we have left once we factor out this thing is g of x plus dx minus g of x divided by dx. So we have, in a square bracket here, I'll write g of x plus dx minus gx all over dx, and then close bracket, plus, and the same thing I'm going to do over here on the right side. We have the limit as dx approaches 0 of, factoring out this gx here, we have gx multiplied by, over here what we have left is f of x plus dx minus f of x all divided by dx. So f of x plus dx minus fx all divided by dx. This might look familiar to you. This thing and this thing are the two derivatives of the two functions. So here what we're going to do next is use the second property of limits, saying that if you have a product of two functions and you take the limit, it's same as taking the two individual limits and then take the product of them. The limit of the product is the product of the limits. So therefore we're going to do that on the left and say the left part here is equal to the limit as dx approaches 0 of f of x plus dx, this thing multiplied by the limit of the second thing, which is the limit as dx approaches 0 of this whole thing here, which is g of x plus dx minus gx divided by dx, and then this whole thing needs to then be added to the second thing, which once again we're going to break it into two limits. We're going to take this gx out and we're going to take this thing separately. So this is equal to the limit as dx approaches 0 of gx multiplied by the second part, which is the limit as dx approaches 0 of f of x plus dx minus fx all divided by dx. So now finally we're going to take our final answer in this line here. Evaluating this first limit, as dx approaches 0, this dx here is going to approach 0, so therefore f of x plus dx will approach f of x plus 0, which is f of x. So therefore this first limit here is f of x. So we have f of x here. This second limit is the first principle definition of the derivative of gx with respect to x. So this right here is d of gx with respect to x. So dgx by dx. And then that's that. Plus, now we have to evaluate the second part. Over here, gx is a constant relative to dx, because no matter what happens to dx, g of x is going to be g of x. So we can take that out and write just g of x over here. And that needs to be then multiplied by this thing, which is the first principle definition of the derivative of f of x with respect to x. So this is d of fx dx. Now we have what we are looking for. We can write that as a final solution and say as a conclusion that over here what we had on the left, which was the derivative of the product of the two functions, is equal to this thing over here. Writing that down as a conclusion, we have that the derivative of f of x multiplied by g of x dx is equal to the first function fx times the derivative of the second function, which is d gx by dx, plus the first function's derivative, which I'm actually going to rearrange these two and take this to the front, take this to the back, because that's the general format that we write this in. This is going to be the derivative of fx dx times the second function gx, or writing this in the prime notation, this is fx g prime x plus f prime x gx. So there we have the product rule as stated here, proven using the first principles, hence proven. Before we continue to the next rule, let's do one example to show you where this kind of rule could be used. So for the product rule, let's take y equals x times the sine of x, and let's use the product rule to find this function's derivative. So here we have a product of two functions. We have x times the sine of x. If we consider x and sine of x separately, the derivative of x is going to be, since x is x to the power of 1, this is going to be 1 times x to the power of 0, because this is an integer, and then here this 1 times x to the power of 0 is going to be equal to 1. Over here sine x's derivative, as we found earlier, is cosine of x. So then therefore here what we have is a product of two functions. Then the derivative of the two functions dy by dx must be equal to the first function times the second function's derivative, i.e. the first function is x times the second function's derivative cosine of x. This is going to be x cosine of x, plus, and then the first function's derivative times the second function, that's going to be 1 times the sine of x. So therefore over here we need 1 times sine of x, so here this is sine of x. Therefore the derivative of y equals x sine x is x cosine x plus sine x. This is an example of the kind of place that you will need to use the product rule. In practice, of course, you're going to have much more complicated problems to solve where you have to use the product rule, but this is just a simple example to show you that you could use the product rule in something like this. The next rule we need to discuss is called the quotient rule. It is like the product rule, but it involves division. So the product rule involved in multiplying two functions together. The quotient rule involves dividing one function by another. Specifically, what the quotient rule says is that the derivative of one function fx divided by another function gx dx is equal to, and I'm not going to write this in the normal format of writing with d over here, because I don't really want to do that. Instead, what I'm going to do is write it using the prime notation. So using prime notation, this is going to be equal to f prime x times gx minus, and then g prime x times fx all divided by g of x squared. So this is a little bit interesting. It's not the same as the previous one. It's kind of complicated. There's like a minus sign here instead of a plus sign, and then there's this gx squared hanging on the bottom, and here there's another extra condition for this to apply. G of x should not be equal to 0, because if g of x is equal to 0, over here we have a divide by 0 anyway, which means we cannot do it. So therefore we make sure that g of x is not equal to 0, in which case this condition here applies. So now let's prove it. Let's prove how this condition applies. So on the left hand side, we're going to take the left, we're going to take the derivative of the first function fx divided by the second function gx, and we're going to write it using first principles. So what we have is the limit as dx approaches 0 of the function evaluated at x plus dx. So in this case, when you evaluate this function at x plus dx, we're going to have f of x plus dx divided by g of x plus dx, and then minus the function evaluated at x, so it's going to be fx divided by gx, and then whole thing needs to then be divided by dx. So we have this. What we're going to do now is to cross multiply these two and take a common denominator of gx times g of x plus dx. Doing that, what we get here is, I'm going to take this equal sign to the left because we need space for this. This is going to be the limit as dx approaches 0 of, taking the common denominator over here, we need to take this multiple, so we have f of x plus dx times gx, and then over here we have minus f times this thing, so this is minus fx times g of x plus dx, all divided by the common denominator of g of x times g of x plus dx, and over here we have another divide by dx, so we'll take that into the common denominator as well. Taking that up into the common denominator, we have dx times gx times g of x plus dx. So this is what we want to solve. Over here, I'm going to first do some factorizing out. I'm going to take this thing separately, this g of x times g of x plus dx separately. We can do this, of course, because limits work like that. We can take it into a separate limit and multiply the two together and write that this is equal to the limit as dx approaches 0 of, over here we have f of x plus dx times g of x minus f of x times g of x plus dx, all divided by dx, multiplied by the limit as dx goes to 0 of, over here extracting these two factors out, what we have left is gx times g of x plus dx. Now then, let's start evaluating. Over here we can easily evaluate this thing because g of x is a constant relative to dx. No matter what dx is, gx is gx. Over here g of x plus dx as dx approaches 0 is going to be g of x plus 0, which is g of x. So over here this part is going to be 1 divided by gx times gx. So we have 1 divided by gx times gx, i.e. 1 over gx squared. How about the left thing? Well, for the left thing, similar to what we did in the product rule, we are going to introduce and then subtract a common term. So what we're going to do here is going to take this equal sign to the left all the way over here because we need so much space to write this. This is the limit as dx approaches 0. We're going to have the first term normally. We're going to first, I'll write the divide by dx here. The first term we're going to have as f of x plus dx times g of x. But now we're going to introduce the term that we want. We're going to introduce negative f of x times g of x, and then when we introduce this term we need to add it again, so we're going to have positive f of x times g of x, and then over here on the very end we have minus f of x times g of x plus dx. So here I'm actually going to take this function and keep it separately. I'm going to take this whole limit and write this on all the way down as L, and we're going to solve L, resubstitute L and bring the thing back, because otherwise we're going to have to constantly carry around this part over here. It's going to be annoying. So we'll simplify L separately and then plug L back into our formula. So considering L is equal to the limit of this whole thing. So L is equal to, over here what I'm going to do is split this limit in two. We're going to have this part separately and this part separately. So this is equal to limit as dx approaches 0 of the first part. Over here in the first part, we can see in these two factors that I'm taking, there's a common factor of gx on both of these. I'm going to factor out that gx and write this is equal to gx times, and what we have left is f of x plus dx minus fx divided by dx. Again, all of you who have watched the previous video will find this extremely familiar. And then there's a plus the second limit, which is the limit as dx approaches 0 of this bit right here. Over here you can see there's a common factor of fx in both of these. Factoring that out, we have fx multiplied by, and what's left is gx minus g of x plus dx all divided by dx. So that's that. Now then, what we're going to do is start rearranging and evaluating. So here, if we take this gx here, gx is a constant relative to dx, because no matter what dx is, gx is going to be gx, so we can take it out. So this is gx multiplied by, and what we have left is the limit as dx approaches 0 of this thing, which is f of x plus dx minus fx divided by dx. This right here is the first principle definition of the derivative of f of x with respect to x. Plus, over here, f of x is a constant relative to dx, because no matter what dx is, f of x is going to be f of x. And over here, I'm actually going to take a minus 1 out of this thing and put it onto this f of x. So doing that, what we have is negative f of x times the limit as dx approaches 0. Now after taking a minus 1 out here, this negative gx plus g of x plus dx is going to be positive g of x plus dx. This positive g of x is going to be negative g of x. So what we have here is g of x plus dx minus g of x divided by dx. Look familiar? Yes. This right here is the first principle definition of the derivative of gx with respect to x. So now then, writing this in final form, what we have here is gx multiplied by, over here this is the first principle definition of the derivative of f of x, which I'm going to write in prime notation as f prime x. So here we have f prime x, and then plus the negative this thing. So here we have a plus and a minus here. But so here what we really have is a minus, and minus here we have f of x, and this second part here is the first principle definition of the derivative of gx with respect to x, which I'm going to write in prime notation as g dash x. So therefore the limit L is gx times f dash x minus fx times g prime x. So now resubstituting that back into here, we have that the derivative of f of x divided by g of x, which is what we have originally over here on the left, we're going to write the derivative of f of x divided by g of x, which is what we've been trying to look for. This is what we had initially, by dx is equal to L times that other part here. So this is L times 1 divided by gx squared. So we can write that as L times 1 over gx squared, which I'm going to put in brackets as squared. Now then, resubstituting L back in here, we can see this is equal to f prime x gx. I'm writing it like this because this is a common way to note it. F prime x gx minus g prime x fx divided by gx squared. So here we have 1 over g of x squared. This is the quotient rule. And now we have proven the quotient rule. Before we continue, let's take an example and show how we can use the quotient rule to find the derivative. Let's consider a simple one, like let's say x squared divided by cosine of x. And let's try and find the derivative of this function. Over here we have one function divided by another function. X squared is one function and cosine of x is another function. So here we want to find the derivative of x squared and we want to find the derivative of cosine of x. Then we can substitute those values into here and use that to find our answer. So the derivative of x squared is going to give the derivative of 2 to the power of 2 times x to the power of 2 minus 1 or x to the power of 1 or just x. So the derivative of x squared is 2x. The derivative of cosine of x is going to be the negative sign of x. We know this from previously. So then this is the derivative of cosine of x. This is the derivative of x squared. What we have is that the derivative of this rational function here, x squared divided by cosine of x, as in dy by dx, is going to be equal to the derivative of the first function, which is in this case 2x. So here we have 2x times the original function gx, which in this case is cosine of x. So here we have 2x times the cosine of x minus, and then minus the second function's derivative, which in this case is negative sine of x. So we have minus the negative sine of x multiplied by the first function fx, which is x squared. So multiplied by x squared. The whole thing then is to be divided by g of x squared. So g of x is cosine x. So here what we have in the denominator is the cosine of x squared. Doing some simplification, we can see this is equal to 2x cos x, and then this minus minus over here turns into plus. So we have plus sine x times x squared, which I'll actually write in this form as x squared sine x, all divided by the cosine of x squared, which we write as cosine squared x. So therefore this right here is the derivative of the function x squared divided by cosine of x. Now let's move on to the final rule. The final rule in derivatives is something called the chain rule, and it goes as follows. Let's say you have y, x and some other intermediate variable, let's say u. Let's say that y is some function of u, meaning you have some function that when you input u, you output y. And we also have that u itself is a function, let's say g of x. So here we have a chain saying that y is a function of u and u is a function of x. From here, from these two, we can see that if we substitute u into here, we can see that y is in fact equal to f of g of x. So given this condition, given that we have y equals f of u and u equals g of x, i.e. y equals f of g of x, then this over here holds. The derivative dy by dx is equal to the derivative dy by du times the derivative of du by dx. Now some of you might look at this and see, well, isn't it obvious if we just cancel these two, this is going to be equal to dy by dx. No, that's not how this works. Remember, this right here is just notation. This is not a fraction. This is simply denoting the ratio as one value changes relative to another value, i.e. it's a function that gives you how fast one value is changing relative to another value. This right here is not a fraction. However, it does in this case appear to behave like a fraction, but you will see later when we go to higher order derivatives, it does not work in the same way. But for now, you can see this kind of behavior is there. The derivative of y relative to x is equal to the derivative of y relative to u times the derivative of u relative to x. So let's see how we can prove this. On the left side we have dy by dx. Writing dy by dx, dy by dx here is, according to this equation, going to be dy by dx according to this equation is going to be the limit as dx approaches 0 of the function evaluated at x plus dx, so f of g of x evaluated at x plus dx, so f of g of x plus dx minus the function evaluated at x, so f of x of g of x, my apologies, by dx. And these other two things here, this thing and this thing, also have their own ways of being represented. The first thing, dy by du is equal to the limit as du approaches 0 of, in this case, the equation relating y and u is this thing. So here we want to evaluate f of this u at u plus du and u. So here what we want to do is evaluate this at f of u plus du and subtract of it evaluated at f of u, and then all divide by du. Similarly, from this relationship we can get another equation, du by dx, this thing here, du by dx is equal to the limit as dx approaches 0 of in here what we have is g of x over here, u equals g of x. So what we want to do here is evaluate g of x at x plus dx. So g of x plus dx minus g of x by dx. So we have this. Note here we cannot simply have these two limits multiplied together easily because the two limits are of two different variables. So if we want to prove this thing here, we're definitely going to have to do some kind of change of variables. So now let's see how we can do this. In order to do this, we're going to take a step back and consider what we're actually trying to evaluate here. So if I consider these two variables independently, if I consider y and u and x separately over here, I'm going to draw two graphs to consider this thing. Over here, let's say this is the y-axis relative to u and this is the u-axis relative to x. And we have this kind of behavior here. And let's suppose the function of y to u looks something like this and the function of u to x looks something like this. So then, let's assume we are interested in this x over here. This x over here has a corresponding value of u. So let's say this is like let's say x0 or something. It has a corresponding value of u, let's say u0. Let's suppose u0 is this value over here. So this is u0. Then we have a corresponding y value to the u value of y0. So then the corresponding y value to the x value here is y0. y0 corresponds to the x value x0. Now then, considering the operation that we're doing here, this application of limits. On the first graph over here, what the application of this limit here du by dx looks like is to consider a certain distance dx in the positive x direction like this. Consider a certain distance like this. Consider what happens to du, what little change of u occurs when you do that. So here du is this length, and consider this function here, this value here, and this value here. So what we're doing is considering the ratio and how we can find the ratio of du to dx. And then in the second example, what we're doing is considering this same du over here, only now it is in this direction, the same exact du except now it's in this direction, and considering when we change u by this certain amount, what happens to y. So y changes by this amount here. So this is dy corresponding to this value du. Now here, the only really important observation I want you to note is that this du and this du would be the same while we do this operation. If we have some corresponding dx, the du corresponding to this dx is going to be this du here, i.e. these two are the same du, and therefore this dy is directly correspondent with this value of dx over here. And then as dx approaches 0, I want you to note that when this thing gets really close, this point gets really close to our point of interest, the value of du also approaches 0, i.e. I want you to take away from this graph that the limit as dx approaches 0 is identical to finding the limit as du approaches 0 because when dx approaches 0, du also approaches 0. When this point here gets super close to the point of interest over here, du and dx both converge to 0 at the same time. So therefore, writing the limit as dx approaches 0 and writing the limit as du approaches 0 are the same. The other thing I want you to consider is what du actually is. So over here, this other point of x here is x0 plus dx. And then here, this point over here is u0 plus du. But this point is also equal to, according to our relationship, since u was equal to g of x, this point here was g of x0, and this other point here was g of x0 plus dx. So therefore, here the second takeaway I want you to take here is that du is equal to this difference here. This difference here is g of x0 plus dx minus g of x0. So g of x0 plus dx minus g of x0, because what happened here was when we went a certain distance here in dx, we found a corresponding distance du, the corresponding difference of x values is this, and the corresponding difference of y values is this. We are going to use these two identities that we've discovered just by observation in order to solve this equation here using these three equations over here. Here we have equation 1, let's say. Here we have equation 2 and equation 3. So what we are claiming over here is that 2 times 3 is equal to 1. So let's see if that's true. Let's see if that's true, and what we're going to do to see if that's true is take 2 and 3, multiply them together and see if we get 1. So here, unlike the previous two, we're going to take the right hand side and simplify it until we get the left hand side. So let's do that. Doing that, if we take 2 times 3, 2 times 3, what we have on the left hand side is dy by du multiplied by du by dx. And then substituting the limits that we have here, the first limit is the limit as du approaches 0 of this thing here, which I'm going to write down. This is the limit lim as du approaches 0 of the value here of f of u plus du minus f of u divided by du. And then multiplied by the second limit here is the limit as dx approaches 0 of g of x plus dx minus gx divided by dx. So here, writing that down, the second limit here is equal to the limit as dx approaches 0 of g of x plus dx minus g of x divided by dx. Now then, into here, let's apply these two substitutions that we have here. The first substitution saying that the limit as dx approaches 0 and du approaches 0 are the same thing, meaning these are interchangeable. We can replace one by the other. We're going to do that shortly. And furthermore, we're going to replace du with this thing right here. So doing that, what we have here on the left, we're going to replace this limit here as du approaches 0 with a dx approaches 0. This is the limit as dx approaches 0 instead of du approaches 0 of, and instead here, instead of u we're going to substitute gx, and instead of here we're going to substitute that equation that we found over here. So then, substituting that stuff, what we have here is f of, remember that u is g of x over here, u is g of x, substituting that into here we have f of g of x plus du we're going to substitute as g of x plus dx minus g of x. So here what we have is g of x plus dx minus g of x, and we're substituting that in instead of du. And then there's a minus f of u. F of u is f of g of x, so here we can substitute minus f of g of x, and then the whole thing here needs to then be divided by d of u. So du here is g of x plus dx minus g of x. Substituting that in as well, we have here g of x plus dx minus gx over here. This whole limit needs to then be multiplied by the second limit here, which is the limit as dx approaches 0 of g of x plus dx minus gx divided by dx. Now then, here we have a product of two limits. Recall that the limit of the product is equal to the product of the limit. So therefore, we can turn this product of two functions into a single product of a function. We can do this only because the two limits are the same exact limit. They are both going to the same exact value. So now, doing that, what we have here is this is equal to the limit as dx approaches 0 of the product of this function and this function. Doing that, what we have here is f of, and over here simplifying the inside here, this gx cuts with this negative gx, leaving us only g of x plus dx. So what we have here on the inside is f of g of x plus dx, which I'm going to write as f of g of x plus dx. And then we have minus f of g of x, which is, I'm going to write as minus fg of x. Divide by, over here we have g of x plus dx, minus g of x, which needs to then be multiplied by the second limits function, which is g of x plus dx, that's not a dx, g of x plus dx minus gx divided by dx. Now observe here, we have g of x plus dx minus gx here, and g of x plus dx minus dx here. Neither of these are equal to 0 because over here we have dx approaching 0, not dx equal to 0. So therefore, g of x plus dx is not equal to g of x. So this is not equal to 0 and this is not equal to 0. Since these two are not equal to 0, we can cancel them out as this, like follows. So here, cancelling those out, what we are left with is the limit as dx approaches 0 of this thing is all that's left on this thing's numerator, and dx is all that's left on the right side. So here what we have is f of g of x plus dx minus f of g of x by dx. What is this right here? Well, look at equation 1. Equation 1 says that dy by dx is equal to the limit as dx approaches 0 of f of g of x plus dx minus f of g of x divided by dx, which is exactly what we have over here. So therefore, finally we can conclude that this is equal to dy by dx. Hence proven. Writing this as a conclusion, we can see that left hand side is equal to the right hand side. The left hand side is dy by du times du by dx, and the right hand side is dy by dx. Therefore, dy by dx is equal to dy by du times du by dx. This right here is the chain rule. This is the chain rule for first order derivatives. We get more complicated versions when we have higher order derivatives, but we're not going to talk about that yet because we have not reached higher order derivatives yet. But the only thing I want to stress here is that these are not fractions and this is not fractional multiplication. You cannot do this and cancel these out. That's not how it works. So then, this is the chain rule. Let's now discuss an example of how we can use the chain rule and proceed to our next topic. So then, for this thing, let's consider a simple example like, let's say, y equals, and we'll put here the sine of x squared, let's say. Over here we can see the sine of x squared is a compound function, as in a function of a function. Over here, if I replace x squared with u, like let's say let u equal x squared, we can see that y is equal to the sine of u and u is equal to x squared. So over here we can see the format of y being a function of u and u being a function of x. Over here, actually, practically when you're doing this, you do not have to do this. You do not have to add a u and like write something like let x u equals x squared or anything. You can do it in the head, and it is accepted to do things like this in the head. But I'm not going to do it in the head for this example because I need to teach you here. So we're going to do it step by step. Over here, what we're interested in here is dy by dx. So here what we're interested in is dy by dx. Dy by dx according to the chain rule is equal to dy by du times du by dx. So here, finding dy by du. Over here, according to this first equation, we know that the derivative of sine of anything is equal to the cosine of that thing. So dy by du here is going to be equal to the cosine of u. Substituting that in, this is equal to the cosine of u multiplied by, and du by dx here, the derivative of x squared is 2 times x to the power of 2 minus 1, or 2 times x squared, 2 times x to the power of 2 minus 1 is 2 times x to the power of 1, which is 2 times x. So here, the derivative of this thing, du by dx, is 2x. So here our answer is 2x times the cosine of u. However, here, u was only a placeholder variable. We do not want u in our final answer. So instead of u, over here, we're going to be substituting this value back into here, which is x squared. So finally, our final answer is going to be dy by dx is equal to 2x times the cosine of x squared. This is our final answer. This rough work in the middle would not be needed in an exam style answer. You would only need the initial step and the final step. Perhaps you might need to state the chain rule in the middle. It might be recommended. But in general, you do not need to write out this part here. It would be advisable for you to do so if you are getting trouble, like if you cannot handle the operation that's happening here, you can put an intermediate variable and solve it like this. However, I would recommend that you avoid this and instead do it directly. So here what I mean is, going from here to here, I would recommend that you do this in one step or potentially two steps if you need it. So that's it for the three rules. We have discussed the product rule, the quotient rule, and the chain rule. So writing these three as a final summary, what we have is the derivative of a product of two functions f of x multiplied by g of x dx is equal to fx g dash x plus f dash x gx. And then we also discussed the quotient rule, which is the derivative of f of x divided by gx, which is going to be equal to f dash x gx minus g dash x fx divided by g of x squared, provided that g of x is not equal to 0, because otherwise we would have it divided by 0. So provided that g of x is not equal to 0, this equation holds. And the final rule we discussed is that if we have some intermediate variable, then we can say that dy by dx is equal to dy by du times du by dx. So over here what we have is the product rule. I'm going to label them as the product rule, the quotient rule, and the chain rule. So before we continue, we're going to derive one last thing. This thing is actually derived from the chain rule. It is a special case of the chain rule, and it relates dy by dx to dx by dy. So considering that, we have that dy by dx is equal to dy by du for some intermediate value u times du by dx. This is what the chain rule states. What we are going to try to prove is that dy by dx is equal to 1 divided by dx by dy, i.e. the derivative of y relative to x is 1 divided by the derivative of x relative to y. In order to prove this fact, we are going to be using the chain rule. So let's consider something like this. We have y is equal to f of x and x is equal to some intermediate value, let's say u. Given this, we can see that over here, using these two, we can see that y is also equal to f of u. Now then, I'm going to write dx by du using the chain rule. Using the chain rule, we know one variable relative to another variable is equal to that variable relative to some third variable, which is I'm going to write as dx by dy times this relative variable dy relative to our other variable du. So this relationship has to hold for this thing here. What is dx by du? Well, x is equal to u, so therefore dx by du is equal to 1. Over here we have dx by dy here, which I'm going to leave as dx by dy, and over here we have dy by du. Since dy by du and dy by dx are both equivalent to each other, since x is equal to u, we can replace this with dy by dx and it will be the same exact value. Therefore we have here 1 is equal to dx by dy times dy by dx. And now finally we can see from this thing, dividing both sides by dy by dx, that dy by dx by dy, that dy by dx is equal to 1 divided by dx by dy. Again, I need to emphasize, these are not fractions. It just happens that here the behavior looks like what we would expect when we have fractions. This does not work for what we call higher order derivatives, which we haven't gotten to yet, but I want you to note, this is not fractional multiplication happening here. We are not dividing 1 by dx divided by dy, which is why we get dy by dx. Rather, it's a different process, but over here it seems that it behaves the same way. So now that we established that, let's prove 3 new derivative identities that we couldn't prove earlier without these 3 rules. The derivative identities we are going to prove are y equals sine inverse x, y equals cosine inverse x, and y equals tan inverse x's derivatives. First off, let's start with y equals sine inverse x. This can be written as x is equal to sine y provided that x is within the valid range, because anyway if x was not within the valid range, sine inverse x would not be a proper function. So therefore over here we need sine inverse x's values of input, as in x, to be between -1 and 1. So here, unlike in previous cases where we had any domain we could put any inputs, over here for this thing we're only going to allow x's between -1 and 1. So now we have this. So here, given this relationship, we can see if we take dx by dy in this case, we know what this is because the derivative of sine of something is equal to cosine of that something. So in this case, since we are measuring relative to y, we're taking the derivative relative to y, this value is equal to the cosine of y. So now then we have that dx by dy is equal to the cosine of y. Since we just found that dy by dx was equal to 1 divided by dx by dy, we have that dy by dx is equal to 1 divided by, and over here what we have is the cosine of y. So we have 1 divided by the cosine of y. Now then, we're only going to do one more step. We're going to write the cosine of y in terms of the value we know, which is the sine of y. We know from previous videos, if you haven't checked that, check this out here, this video on the top right. We know that sine squared of anything plus cosine squared of that same thing is equal to 1. Using this fact, we can say that cosine squared of y is equal to 1 minus the sine squared of y. So over here, the cosine of y is the square root of cosine squared y, so this is equal to 1 divided by the square root of cosine squared y, which is 1 minus sine squared y. And finally, for the final substitution, we're going to substitute sine y as x. So here what we have here is 1 divided by the square root of, instead of sine y, we put x. So here we have 1 minus x squared. Therefore, as a final conclusion, we can say the derivative of this function here, which we have as sine inverse of x, so we have to write d sine inverse x by dx is equal to 1 over the square root of 1 minus x squared for the valid range of x, i.e. x is between -1 and 1. So therefore, this is the derivative of sine inverse of x. Let's now move on to the next one, which is y equals cosine inverse of x. So going to that one, we'll actually do it on the same page since it doesn't take that much space. This one has a similar method to do it. We have y equals cosine inverse x. Again, this needs to be for the valid ranges. So if we have y equals cosine inverse x for x's between -1 and 1, so x between -1 and 1, given this we can say that x is going to be equal to the cosine of y. Now then, taking the derivative of both sides, dx by dy, as in the derivative of x relative to y instead of y relative to x, we have the derivative of cosine. The derivative of cosine, as we found earlier, is negative sine, so here we have negative sine of y. Therefore, if we have dx by dy being negative sine of y, dy by dx must be 1 over that, as in 1 over negative sine y, which I'm going to take the negative up and say negative 1 over sine y. Once again, using the identity that sine squared of anything plus cosine squared of that same thing is equal to 1, we can say this here, this is equal to -1 divided by the square root of 1 minus the cosine squared of y. And finally, as a final statement, since the cosine of y is equal to x, we can substitute x into here and put x as this thing, so that we have -1 divided by the square root of 1 minus cosine of y is x, so here we have x squared. Therefore, in this case, we have that the derivative of cosine inverse of x dx is equal to -1 divided by the square root of 1 minus x squared, of course, provided that x is in the valid range, so x between -1 and 1. Hence proven. And there's one more we need to prove, that is the tan inverse case. So here we need to prove that the derivative of y equals tan inverse x is what? So here we have y equals tan inverse x. Unsurprisingly, we're going to use the same exact method that we just used earlier. We're going to write this as x equals tan of y. Now here in this case, tan inverse can actually have any input along the real numbers. So therefore, x is going to be anywhere between negative infinity and infinity. So x is between negative infinity and infinity. Now then, taking this thing, we know what dx by dy is. From the previous video, we found that the derivative of tan of something is equal to secant squared of that thing. So this is equal to the secant squared of y. So we have the secant squared of y. So therefore, dy by dx is going to be 1 divided by this. So it's going to be 1 divided by the secant squared of y. We are going to use a different identity here in order to simplify this and write this in terms of tan of y. We know, and we've solved this previously. If you haven't checked that, check this video again. Actually, I don't think YouTube can allow me to link the same video twice. So go ahead and check sine squared plus cosine squared equal to 1 video and come back. So here in that video, we found that the secant squared of any value is equal to 1 plus the tan squared of that value. So here this is equal to 1 plus the tan squared of that value. Substituting that into here, what we have is over here 1 plus the tan squared of that value, which in this case is y. So here we have 1 divided by 1 plus the tan squared of y. Now for the final statement, what we're going to do is substitute tan y as x. Doing that, what we get is 1 divided by 1 plus x squared. Therefore, the derivative of tan inverse x, i.e. d tan inverse x by dx, is equal to 1 divided by 1 plus x squared. For the valid x's, in this case of course, any x between negative infinity and infinity will work. So basically, any x will work for this one compared to the other two which had limited domains of x between negative 1 and 1. So that's that for these three. And now let's go on to exponential functions and logarithms. Our next topic of discussion is going to be the exponential function e to the power of x and its inverse function, the natural logarithm ln of x. Now here, before we continue, I want to show you this notation. ln is meant to represent the logarithm base e of x. The logarithm base e of x is identical to saying ln of x. It's just that we like this thing because it's much easier to write, much shorter than log base e, and it's much more elegant. It places an importance on the value e. This stands for the logarithm natural. ln logarithm natural. It is the natural logarithm. Here the natural logarithm is the inverse function of e to the power of x. So therefore, e to the power of logarithm of x is equal to x, and the logarithm of e to the power of x is also equal to x. The logarithm, natural logarithm ln, is the inverse function of e to the power of x. So then, carrying on, let's find the derivatives of e to the power of x and the natural logarithm of x. If you haven't seen the video already, check this video out in the top right here, all about e to the power of x. E to the power of x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the power of 4 over 4 factorial plus all the way to infinity. There are an infinite number of terms here, and all of them summed together gives us e to the power of x. This kind of series here is what we call a Taylor series. We're not going to discuss Taylor series. In fact, I proved this Taylor series in a different video. Check that one out if you want. But for now, we're going to continue with this thing and only talk about this Taylor series here and use it to find the derivative of e to the power of x. So here you can see, if I take any finite portion of this Taylor series, it is a polynomial. Here we have integer powers of x and coefficients on them. So then, if we consider instead of certain finite quantities of this Taylor series, the infinite Taylor series in its own, we can regard it as being a polynomial and differentiate each of its components based on the way that we found when we were differentiating polynomials. So then, doing that, on the left hand side we have the derivative of e to the power of x dx. This must be equal to the derivative of all of these terms. Remember that the derivative of some functions summed together is the sum of the derivatives of those functions. I'm going to skip that step and directly write this as the derivative of 1 dx plus the derivative of x dx plus the derivative of x squared over 2 factorial dx plus the derivative of, we're going to do one more and end it there, x cubed divided by 3 factorial divided by dx continuously. So here, let's try and evaluate each of these and see what we get. The derivative of 1 is going to be itself just 0, because 1 is 1 times x to the power of 0. taking this thing using our knowledge of x to the power of n's derivative, this is going to turn into 0 times x to the negative 1, which is going to be 0. So therefore the derivative of 1 dx is going to be 0, plus the derivative of x with respect to x is going to be 1, plus, and all of these terms after that have the form of x to the power of r divided by r factorial. We are going to be differentiating all of these at the same time by differentiating their common form. So here r is some integer, which means to this top part we can apply our integer differentiation and say that this is going to be differentiated into r times x to the power of r minus 1 divided by, and here we have r factorial. Now here I'm going to do something. I'm going to consider r factorial and say, since r factorial is r times r minus 1 times r minus 2 all the way down to 2 and 1, we can write this thing as being equal to r times x to the power of r minus 1 divided by, and we can write r factorial as r times r minus 1 factorial. Now cancelling out these two r's, we are left with x to the power of r minus 1 divided by r minus 1 factorial. Now here we can see what we get is x to the power of r minus 1 divided by r minus 1 factorial. Applying that to all of these terms here, this term has r equal to 2, so therefore its value should be x to the power of r minus 1 or x to the power of 2 minus 1 or x to the power of 1 divided by 2 minus 1 factorial, which is 1 factorial, which is 1, so divide by 1. So we're going to leave that as is. The next term after that has r equals 3, so it's going to be x to the power of 3 minus 1 divided by 3 minus 1 factorial, or x to the power of 2 divided by 2 factorial. The next term after that, which I haven't written, is going to have r equals 4, so its value on when differentiated is going to be x to the power of 4 minus 1 or x to the power of 3 divided by 4 minus 1 factorial or 3 factorial. The next term after that is going to be x to the power of 4 over 4 factorial and so on. Now notice here, what we had up here for e to the power of x is 1 plus x squared divided by 2 plus x 2 factorial plus x cubed divided by 3 factorial plus x to the power of 4 divided by 4 factorial and so on. When we differentiated this, what we got is 0, which we can ignore, and 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the power of 4 divided by 4 factorial and so on, which is exactly the same as what we had up here. So therefore this infinite sum down here is also e to the power of x. Therefore we can see that the derivative of e to the power of x with respect to x is equal to itself e to the power of x. In fact, e to the power of x is the only function, and well, there's a whole family of functions, but e to the power of x is a unique element of this thing where its derivative is itself. What I meant by the family of functions is actually the derivative of any constant c times e to the power of x with respect to x is in fact itself as c times e to the power of x for c element of the real numbers. The reason for this is that when we have a constant times a function, its derivative is that constant times the derivative of the function. The derivative of e to the power of x is e to the power of x. Multiplying by the constant, we get c times e to the power of x. So therefore, for any constant c, that constant c times e to the power of x's derivative is itself c times e to the power of x. So we have an interesting property. In fact, these family of functions are the only functions that have this property. The derivative of the function is itself the same exact function. Now that we've done that, let's do the derivative of the logarithm of x. So to take the natural logarithm of x, let's consider y equals the natural logarithm of x. There's one way to do it where we can take the exponent of both sides. There's another way to do it where we can take it from first principles. Let's do the exponent way because it's quite nice. Over here what we're going to do is take e to the power of both sides. So here on the left side we're going to have e to the power of y is equal to e to the power of the natural logarithm of x. Since e and natural logarithm of x are perfect inverse functions, on the right hand side we can write this as just x. So therefore we have e to the y equals x. Rearranging this in so that we have the subject on the left side, we have x equals e to the power of y. Now taking over here d of x with respect to y, dx by dy, since here we have e to the power of y and we found that e to the power of something is itself going to be the same exact function, the derivative of e to the power of y with respect to y is going to be e to the power of y. So now here we can see dx by dy is e to the power of y. Using our rule from earlier, we can see that now dy by dx must be 1 divided by this. So dy by dx must be 1 divided by e to the power of y. And now taking this final thing, we know that e to the power of y is equal to x. So therefore, the derivative of the natural logarithm of x dx is equal to 1 divided by e to the power of y, which is x. So 1 divided by x. Hence proven, but there is a different way to do it, which is more basic and more reliant on only first principles. So we'll do that one also, but note, I think in most contexts this would be acceptable as an answer other than when you're dealing with complex numbers. We'll get to that later, but for now let's go to the first principle derivation of the derivative of y equals ln x. So going down here, let's take some space and let's write down y equals the natural logarithm of x. So then, in the most basic sense, using first principles, dy by dx is the limit as dx approaches 0 of the logarithm function at x plus dx minus the logarithm function at x, all divided by dx. So since the natural logarithm behaves as any other normal logarithm, it follows the normal logarithm rules. If you don't remember the logarithm rules, you can check this video here on the rules of logarithms and indices. So then, if it follows the normal rules of logarithms, it must follow the rule that the log of a minus the log of b is equal to log of a divided by b. Given that it follows this rule, we can write over here that this is equal to the limit as dx approaches 0 of natural logarithm of x plus dx divided by x, and then that whole thing divided by dx. So now here we can see we have x divided by x here and a dx divided by x here. So I'm actually going to take that thing out and write this as the limit as dx approaches 0 of the natural logarithm of 1 plus dx divided by x divided by dx. Now we are going to do a change of variables here. We are going to change this variable up into a different format. Doing this change up, we are going to write this thing as, let's say, n. Let's say n is equal to dx by x. Using this, let's say let n is equal to dx by x, we can see since x is some finite value, when dx approaches 0, we have 0 divided by some finite value, so therefore n is also going to approach 0. So then we can see that the limit as dx approaches 0 is also going to be equal to the limit as n approaches 0. So we can replace that. Replacing that, we can see that dy by dx in this context is equal to the limit. Instead of dx, we can substitute n. So as n approaches 0 of the natural logarithm of, here we can substitute instead of dx by x, we can substitute n. So we have 1 plus n, and then divide by, instead of dx, we can see from this equation, we need to substitute n times x. So here we can substitute n times x. Now we're going to again change the variables a little bit, but before we do that, we're going to extract this x outward. Since x is independent of n, i.e. no matter what n is, x is going to be x, we can take it out of this limit. Going to the next page, we can write this as dy by dx equaling 1 over x times the limit as n approaches 0 of, over here, this divide by n I'm going to take to the front as 1 divided by n times the natural logarithm of 1 plus n. Now we're going to do one more variable change here. We're going to consider, like, let's say let, and we're going to say some other value, let's say h is equal to 1 divided by n, and consider what happens here. So here we can see as n approaches 0 from the positive side, h is going to approach positive infinity, and as n approaches 0 from the negative side, h is going to approach negative infinity. So on both sides we have some infinity, it's one or the other. So then over here we have dy by dx is equal to 1 divided by x times, and here we have two cases, the positive case and negative case. We'll just call this thing L here and solve the positive case and negative case separately. So when we have h is equal to 1 divided by n, as we discussed, when n approaches 0 from the positive side, h approaches infinity from the positive side, so it approaches positive infinity. However, if we have n approaching 0 from the negative side, then we have 1 divided by 0, but we have negative that, so this is going to approach negative infinity. Taking those two separately, for positive side, we're going to have the limit as h approaches positive infinity of, and then substituting over here, instead of 1 divided by n, we're going to substitute h times the natural logarithm of 1 plus, instead of n, we're going to have to substitute 1 divided by h. Now here I want to direct your attention to the fact that over here we have a constant times a logarithm. You will know that when we have this kind of thing, this is the same as taking this thing to the power of that number, as in the logarithm of a to the power of b is equal to b times the logarithm of a, and vice versa. This is the same for all logarithms, therefore it's true for the natural logarithm as well. Using this, we can rewrite this in the form of the limit as h approaches positive infinity of the natural logarithm of the value of 1 plus 1 divided by h to the power of h. Now, we know what this thing is from the previous video on e. If you haven't checked that out, check it out. The limit as h approaches infinity of 1 plus 1 divided by that value to the power of that value is equal to e. So this right here inside is equal to e. So this is equal to the limit as h approaches infinity of this value, which is going to give us e. So this is equal to the logarithm of e, i.e. e to the power of 1. The logarithm of e to the power of 1 is simply the value on top, which is 1. So therefore, considering the right hand side limit as h goes to positive infinity, we have 1 as the answer. Now we have to also evaluate the other side and make sure that both sides agree. So evaluating the other side, we have L equals the limit as h approaches negative infinity of h times the natural logarithm of 1 plus 1 divided by h, and then this is going to be equal to the limit as h approaches negative infinity. Again, taking that same rule, we can take this as a power on top and write this is equal to the logarithm of 1 plus 1 divided by h to the power of h. Now this I actually didn't discuss within my previous video, but even at negative infinity, 1 plus 1 divided by h to the power of h at negative infinity is also equal to e. So this is also equal to this internal part here is also equal to e. So here what we have is the logarithm of e to the power of 1, which once again is equal to 1. So since the two limits are agreeing, then L is definitely equal to 1. So therefore we have L is equal to 1. Hence, substituting that back into here, we have dy by dx is equal to 1 divided by x times L, where L is 1, so times 1, i.e. 1 divided by x. Hence, the derivative of the logarithm of x, the natural logarithm of x, dx is equal to 1 divided by x. Hence proven. So that is actually it for this video today. As I said, this lesson is far too long. We're going to need another third part to discuss that. It should probably be out by the time you're watching this video. If not, you'll have to wait a little bit. But yeah, that's the end of this video. In this video, we discussed the product rule, as in if you have the two functions multiplied together, what their derivative is. The quotient rule, as in one function divided by another function, what its derivative is. And the chain rule, as in when you have a third variable in the middle, you can find that dy by dx is equal to dy by du times du by dx. Then we discussed, using these three rules, how we can find the derivatives of the three inverse trigonometric functions: sine inverse for x between -1 and 1, cosine inverse for x between -1 and 1, and tan inverse for any x in the real numbers. And finally, we discussed e to the power of x and natural logarithm of x and their derivatives. So that's it for this video now. I'm going to end this video and you will have to check the next video for the final end of this lesson. Thank you for watching and goodbye.